Labrīt, dāmas un kungi. Mani sauc Edijs Poga. Esmu uzvienāts advokāts un Biedrības Latvijas Tiesību institūts direktors. Biedrība Latvijas Tiesību institūts ir neatkarīga, nepolitiska, nevalstiska bezpējas apvienība, kurā apvienojušās personas ar kopīgām interesēm par Latvijas tiesībām un to attīstību. Institūts vienmēr un visur darbojas neatkarīgi un stāv ārpus politisko partiju vēstās politikas. Institūta misija ir veicināt Latvijas Republikas kā demokrātiskas taisnības un tiesību valsts tālāk atjaunošanu, nostiprināšanu un attīstību. Šogad aprit 10 gadi, kopš mēs esam aizsākuši ārvalstu akadēmiķu vieslekciju programmu Rīgā. Šī gan ir 9. lekcija programmas ietvaros, jo 2 gadu garumā mums bija neliela pauze sakarā ar pandēmiju. Bet šis ir tāds tā kā jubilejas gads. Es atgādināšu, ka mēs startējam 2014. gadā ar profesoru Viša lekciju par tirgus varu. Lūk, šodien pie mums viesojas Amsterdamas Universitātes pasniedzējs un Moldovas Nacionālās bankas padomnieks Mihnea Constantinescu. Viņa vieslekcijas tēma būs mākslīgais intelekts, mašīnu mācīšanās un ar to saistītie juridiskie un ekonomiskie izaicinājumi. Šodienas viesim ir doktorgrāds finansēs no Cīrigas Universitātes, Šveices Finanšu institūta. Un viņa pētnieciskās intereses skar daudz dažādas ekonomikas un finanšu jautājumus, kā arī modernās tehnoloģijas, mākslīgo intelektu un digitālo transformāciju. Pavisam nesen viņš ir publicējis arī rakstu par Centrālo banku digitālajām valūtām. Žurnālā The European Journal of Law Reform, kur es visiem ierosinu vēlāk iepazīties, ja ir interesi par šo interesanto tēmu. Mākslīgais intelekts šobrīd ir atrodams, tiek pielietots visdažādākajās jomās, sākot ar sadzīves tehniku, sakaru ierīcēm, beidzot ar medicīnu un kosmosa tehnoloģijām. Tas ietekmē veselu virkni ar mūsu lēmumiem ikdienā, un tā skaitā tas skar arī tāds fundamentāls process, kā demokrātiskie procesi valstī. Līdz ar to tas ir diezgan nozīmīgs, lai arī eksotisks sarunu priekšmets apspriešanai. Ja? Tas arī līdz ar to rada veselu virkni ar juridiskiem izaicinājumiem, visdažādākos juridiskos jautājumos, sākot ar privātu tiesībām, beidzot ar valsts un pamattiesībām. Savā ziņā mēs varam būt lepni ar to, ka Eiropas Savienība ir pirmā, kas ir radījusi un pieņēmusi nesen pirmo detalizēto visaptverošo mākslīgā intelekta tiesisko regulējumu, tā saucamo Eiropas Savienības mākslīgā intelekta aktu. Un, protams, kad mašīnu mācīšanās mākslīgais intelekts pašlaik ir gan globāli, gan Eiropas līmenī, gan arī pie mums nacionālā kontekstā viena no tādām karstākajām apspriestajām tēmām starp tiesību pratējiem un politikas veidotājiem. Un šīs ieslekcijas mērķis ir nest pienesumu arī šai diskusijai. Ja? Latvijas Tiesību institūta vārdā es vēlos pateikties mūsu tradicionālajiem atbalstītājiem, augstākajai tiesības senātam, Latvijas Vienāto advokātu kolēģijai, Konkurences padomē, jurista vārdam, Rīgas Latviešu biedrībai, Eiropas Savienības tiesību asociācijai, LO juridiskajai fakultātei, kā arī advokātu birojam Eliks Kļaviņš, Sorainen, Everšets Sutherland, Bitāns un PwC Legal. Kā parasti ieslekcija būs 2 stundas bez pārtraukuma. Galā varēsiet uzdot jautājumus un saņemt atbildes. Tas arī viss. Paldies. Un lūdzu sagaidīt tradicionāli viesi ar aplausiem.
Morning, everyone. So I didn't understand the word Eddie said. I have to agree with everything he said. We leave it at that. So we're supposed to spend almost 2 hours together, so I'll try to make this entertaining. It's not always because we have to talk about law and technology. And this put together usually give us very, very special mixes, and I'll show you why that's the case. So this is a very, very brief introduction. We're going to talk a little bit about why data has changed so much the way we understand how law is done. What is the role of machine learning and AI in this? We're going to draw some parallels to the, let's say, 5 years revolution in blockchain that has produced a lot of contradictions and a lot of new regulation. We're going to talk about decentralized governance and generally about business model innovation. I'm structuring it like this, not as a traditional, perhaps legal talk, because a lot of the things that law has to do is to react to how technology evolves and how the consumer adopts or adapts to that. And this is a little bit in the middle where we don't want to let technology whatever it wants, but also we don't want to kill its potential for innovation. So when we talk about innovation or digital innovation, we have to put some definitions down. So there's two different ways to look at this. The first one is the first wave of digitization, the fact that we had computers and devices that could store data and transmit data over the internet. So the first steps to where we are today is this digitization, which is this conversion of analog artifacts, text, image, sound, into digital representations. What computers understand is just zeros and ones. So computers can store and transmit zeros and ones, and they can convert text, image, sound into zeros and ones. They send them over the internet, and they reconvert them back to text, image, and sound. This was the first stage that led us to where we are today. And this is just digitization. So we're just transforming the stuff we have in a digital representation, something that the computer can store and transmit. Digitalization is something much broader, because it means that we take this new technology and we transform the way we conduct business, very generally understood, both in private and public domain. So we're reshaping activities, we're changing their nature, we're enlarging their objectives. If you look at the private sector, digitalization meant lower costs, it meant new revenue streams, entirely new products, and entirely new markets. If you look at the public sector, it's also lower costs. It has the potential to increase transparency and accountability. And this digitalization is enabled by new technology, where we have digital eyes and ears, we have digital memory, and we have what we could call a digital brain, although I'll make an argument that's not really what AI is. And together with this, we have new business models, such as platform solutions. Before, markets would be going from your physical building to something that's over the counter in finance. Now we have more or less everything set up as a platform. We meet online to order a cab, we meet online to order food, we meet online to make an argument, and so on and so forth. At the heart of all this stays data, where volume, detail, timeliness raise questions about privacy, about ownership, and about usage rights. This was true for the first, let's say, part of this digitalization wave, which was the 2001, 2002. It's also valid if we talk about the blockchain, cryptocurrency, stablecoin discussion, and it's also true for the artificial intelligence episode. Security and privacy of data stored and transmitted over the internet become a focal point, and we need new rules and new regulations to account for this. Cybersecurity was not at the forefront unless you were a technology company. Now everybody has to worry about cybersecurity, whether you sell financial products or you sell a soup, because the customer's details, financial information, and so on and so forth need to be treated with the utmost care. And this new volume of data also brought new business models, which are simply built around data streams. It's not just enough to say, oh, I know what happened last year in this market. These platforms work by having constant access to these data streams of customers, transactions, and so on and so forth. So just to tell you that this is not something that's just a speculation. This is an article I wrote in 2008, which is responding to data is the new oil. The counter argument I'm making here is it's not really the new oil until we're asking who's drilling for it. Because data was supposed to be this transformative new resource that creates a new economy. And my argument in 2018 here is that this part can become useful if it's properly managed. The way in 2018 I was seeing this is that this data is only going to become feeding for AI algorithms. And the solution that I'm sort of looking at is to simply recognize that once we understand that data has this value, the only actor able to stand between a large corporation harvesting and using this data and the final user is the state. And the way the state can do this is by simply recognizing that data has value. One way to do that is to allow you to pay your taxes in data. This might sound a little bit counterintuitive, but keep in mind that what we're doing, every click we have, everything we do ends up in value-added tax when that platform sells a taxi ride, a hotel room, if we buy from Amazon, and so on and so forth. So this is just, it's a very quick snapshot showing you this is an ongoing stream of changes that go through our economy, where the regulators will need to think very, very creatively in a completely different way, simply because it's not just something that happens over a 2 or 3 year, it's not just something that happens in a market, it's a completely new model to look at markets. Now, just to understand what this means and why this transforms economy. This is a cautionary tale of digitization without digitalization. These two words kind of have the same root, so what exactly is their difference? There's two companies, one digitized, the other one digitalized. Some of you maybe remember at the beginning, Yahoo had its email service, but also had a search engine. And Yahoo was on the market way before Google. What Yahoo did when they started to think about how to organize large amounts of data was to say, let's digitize. So they went to a library, they look at how material is assembled and categorized and cataloged, and say, let's take that catalog system and turn it into a 0 and 1 catalog system. So when somebody looks for something, it's going to start saying, oh, I want to look for a book on mechanical engineering. It's going to go at the engineering, and it's going to look through all the engineering titles, and it's going to find the mechanical, and it's going to give you whatever, 20 titles. But what it did something that was very mechanical. It was simply translating a process on paper that was designed because there was no technology, and it brought it into a 0-1 world. Why was this taken over by Google? Google understood that when you're looking for something, you want to find something that's relevant. So what Google introduced was relevance in the search engine results. It digitalized simply by saying, you're looking for information, we have technology, now we can search for information and return information in a completely different way than a typical librarian. We're not just giving you titles, we're giving you titles that other people think are useful. And they did this in a very simple way. They said, let me see, for example, for a particular title, for a particular website, what other websites, what other title reference that particular website or book. The more referenced you are, the more relevant you become, the higher you're on your ranking page. Okay? And what happened is that Google took over, and Yahoo, even though it had the benefit of being the first, didn't do very much with that search engine. This is one example, but keep in mind that everything else around it is starting to become digitized. So we have digitalized in years across our cities, in our smartphones, that produce vast amounts of data that before were not available. These amounts of data now are processed by algorithms that run constantly, and this is where machine learning and AI come in. They can process vision and sound, and they can perform classification, they can perform prediction, telling you who is going to go unemployed or not, who is going to default on a mortgage or not, and it can generate text, image, and sound. This together, so the first and the third, the digitalized in years, enabled platform economies. These are ecosystems of two-sided markets that lock users in through networking effects. And again, this is a novelty perhaps as compared to traditional markets, where if you didn't like a particular market, a particular seller, a particular product, you would simply go to another physical market. Now that physical markets don't exist anymore as segregated. Networking effects simply say that these markets, once they find a proper solution, they grow so large that it becomes almost impossible to leave them. So these networking effects create some lock-in for users, which make it very difficult for the regulator to come in and say, oh, this is not right, or this is, the alternative might be even worse for the final user. I'll just give you two examples of what I mean by digital eyes and ears, and how broadly this can be understood. Recently, satellite data has become very cheap. Before, it used to be extremely expensive and not even available to the public. Nowadays, if you go on NASA's website, they have a suite of products that's called Black Marble. You create your own account, and it gives you nightlight intensity of any place on Earth. Now, this might sound like it's not a big deal. What do I care about nightlight intensity? Well, there's a lot of research that goes on using this data to forecast and nowcast economic activity. If you tell me how bright city lights are, I can tell you what its GDP and income is. If you're going to a country that doesn't have statistics or has spotty statistics, or you have doubt about them manipulating their statistics, you can use this data and compare it to other countries that have good data and nightlights and see what those nightlights from the country that you're looking at tell you about what their income and GDP should be. This was used during the war. There is the paper together with two co-authors in 2023, where in 2022 we were looking at nowcasting Ukrainian GDP without having any official statistics. So this is one of the sources that we use. The top picture is nightlights where you can see the contour of Ukraine. The little red rectangle is Kyiv. On the bottom, you see it 1 week after the invasion. What is this picture? This picture actually is nothing else but a matrix, a large table of zeros and ones. Each of its pixels, each square, it's called a pixel, has a value that registers the luminosity intensity in that pixel. 0 means black, 100 means extremely bright. So this is the map, the light map, if you want, of Kyiv. City center has very high luminosity levels. Further away from the city center, you have less luminosity. And this is after the invasion. Okay? Now, this is your input data, and this is how it looks over time. You can split this up by regions, and that's exactly what we did. You can create so-called time series. You can look how luminosity evolves over time, and you can link this luminosity to income or GDP. And you see here that areas, these are oblasts, administrative units, that have less luminosity, have less GDP. Kyiv city, with about 25-27% of Ukraine's GDP, stays here with the highest number for GDP and luminosity. And you can use this variation in luminosity to understand, when lights are turned off, how much economic activity have we lost. Okay? This is a very, very, very far away eye. But we have smaller eyes that are even closer to us. Somebody wanted to understand how people sit in a room using some physical principles of how waves interact with objects through space. When we turn on our Wi-Fi, that Wi-Fi sends a wave, a signal. That signal bounces through the room and it turns back to the antenna. That can trace our pose, our movement in the room. This is another way in which you can see, between brackets, very, very detailed information about a person. So this is how to see people through walls using only Wi-Fi signals. And this has turned out to be an extremely useful technology thanks to some research Facebook did on identifying people in a picture. Every time we upload our pictures, they want to understand what you're doing, how many people are there, and so on and so forth. All that technology evolved in very rapid cycles. Every 3-4 years or so, there's another great breakthrough that builds on previous technologies. And this is more or less how you can create from an actual picture, how you recreate the shape of a person, and you realize if that person is sitting, it's standing, or whatever. At least you know how many people are in the room, and so on and so forth. There's numerous more examples like this. This is just to tell you that when we talk about digital eyes, ears, and brain, there are numerous technologies out there that are creating and using this data in extremely innovative ways. Once you have this data, what do you do with it? Well, you can sell it, and that's what happens most of the time. You can also use it to create a model of mathematical function that can answer some very, very precise question, either about a particular user, about a particular product, about a country, or so on and so forth. So these machine learning and AI technologies are computer routines that are able to replicate, automate, and enhance human cognitive function. Of course, there's an argument that they can completely replace them. We can walk through this, and I think there's limits to that, at least for the time being. So when we talk about how machines are able to replicate, automate, and enhance, we have to go back to our very, very first slide that was saying machines can only understand zeros and ones. So when we want to make some forecast about what the price of oil is going to be, when we want to make some categorization, looking at the person and saying this person is going to default or not default on a loan, how exactly are we going to turn this question into something that the computer understands? Well, we have to go back and understand what the computer works with, just zeros and ones. So the first thing we need to do before we do that is figure out how this general recipe of an artificial intelligence machine learning algorithm is set up. So to the questions, do machine learn? The quick answer is no, not really. They're not really learning. This is a misnomer. The long answer is this is a very, very sophisticated, if you want, setup in which you define some functions, you put some parameters in, you play with it until you find the proper parameters that can give you the right answer. Now, this sounds like gibberish maybe for all of you. I'll show you in a minute how easy this can be done. So machines learn via optimization. Optimization is something that you intuitively understand is picking up the best out of a set of solutions. Okay? If you're given a choice, and an objective function, you're gonna just want to pick the one that's best for your interest. Okay? That's very simple. Think about choosing between 5 bank accounts where to deposit your money. You're just gonna choose the one that gives you the best interest rate on it. Okay? What do? You optimize, and your parameter of optimization is the interest rate. It's a very simple thing. Machines do the same, only that they don't optimize over one parameter. They might optimize over millions or billions of parameters, and they do that very fast. Let's see how this works. So first thing first, you have to set an objective for your function. What do I want to achieve with my machine learning algorithm? So if we go back to our idea, I want to make the best out of my money when depositing that in a bank. The same way machine needs to understand what do I need to solve. So the human decides between an implicit or an explicit objective. So the explicit objective can be very well, tell me who do you think is going to default in this pool of 10 or 100 people. If we go to law, tell me who do you think is going to commit a crime over the next 12 months. That's the objective of the machine, to tell you who's the most likely person to commit fraud, a crime, who is going to default, and so on and so forth. That's your objective. You're the human, you set the objective. It's not the machine that chooses this. Once you set the objective, you need to choose data, because remember, these are large functions that feed on large amounts of data. So the human needs to select which data to use for learning. I'm using learning here in the improper way, in the machine learning way. It's not that they learn like we do and then, no, they just pick up some parameters, but we go with terminology. So until now, we chose an objective function, we defined it, we said what it is, we chose the data. Then we go to the computer and we ask our IT colleague to turn that objective into something that the machine understands, and machines understand functions. So this is a mathematical function that you put in, and the machine codifies that and translates into something that it understands. Once you have these three elements, the last element, again, is to optimize. So you go and you tell the computer, with the objective that I gave you, the data that I gave you, and the function that you have, pick those parameters that give me the most out of that function. This is where the machine learns. The machine optimized by choosing some parameters inside that's telling us these are the values that can help you predict who's going to commit a crime, help you predict who's going to go unemployed, and so on and so forth. Okay? It makes errors, and this is something we're going to talk about, but this is more or less what it happens. This last stage, once you run this stage, you can then say the machine learned about this particular program. Now marketing comes and says, oh, this is amazing, machines learn. Remember, the human defines everything. The human defines the objective, picks the data, programs the function, and then presses a button, and then the machine answers to a lot of predetermined tasks. It's not that it just magically learns something that you never thought of. Within the reality that you set for the machine, it can find very useful things, but it's you who sets everything from the beginning. Okay? So let's take this and try a very simple exercise. You are at the courthouse, you have so many files to look at, you want to understand who you can let free because it's not at risk of committing another crime and who not. And you remember something from your statistics classes sometime, and you remember some professor was saying, well, past activity might be a good predictor for future activity. So what you do, you go at each individual case and you say, look, over time, this particular person, this is the number of, let's say, crimes they committed. And you can do this for different types, but let's just keep it with numbers. And what I want to do is to use this past data to understand if this person is going to commit 1, 2, 3, 5, 10 crimes over the next year. Okay? This is a very simple way to look at it. These are actual observations. This is what happened in the past, and you want to make a forecast. Let's say you make your forecast to be the last value. So you're going to do just as bad as you did last year. You broke into 5 homes and stole stuff. That's what you're going to do this year, supposedly. How do I know if my model works well? Well, what I'm doing now, this is a very naive way of predicting. Now I know that machines can learn. Let me take that recipe and talk to my colleague who says, look, it's not that the last number matters. For some people is what they did over the past 2 or 3 years. That's an idea. Okay, let's ask the machine to create for us, to compute for us an error. And what I want to do is to create that function with one parameter, where if I change the parameter a little bit, my function is able to get me better and better predictions in the future. What's that parameter? Well, my colleague just said it's not the last year, it could be the last 2 years or 3 years. Okay? So in some cases, when I'm going to do a forecast, I'm not going to use the last number, this value here, I'm going to use the last 3 numbers. I'm going to take the average. So crimes t minus 3, t minus 2, t minus 1 divided by 3. That's a very simple thing. Okay? But then some other colleague says, wait, it's not 3 years, I think it's 5 years or 7 years. So we have a lot of choices. If we have a lot of choices, that means we have a parameter. So let's do our machine learning thing. We set an objective, which is to predict number of convictions. We choose the data to be past convictions. We codify our function. Remember that the machine doesn't understand stuff that we talk to each other like that. It needs to understand stuff it can work with. And the function we say is use the average number of conviction over past X quarters. That's our parameter. How many quarters to plug in to our function? How do we learn? Well, the computer is going to do one calculation for 1 quarter. It's going to observe an error. It's going to save it. It's going to do a calculation for 2 quarters. It's going to observe another error, and it's going to save it. It's going to do 3 quarters, 4 quarters, 10 quarters if it's needed. All of this saves the errors across all the individuals that we have, and it averages across them. And it's going to tell us that the smallest prediction error might be, let's say, for 3 quarters. That's our optimum. Our machine learned. So we use past data, we set some objective, and the machine searches across all combinations of these parameters that give us the smallest prediction error. This is how machines learn. Is this the right way? Is this the wrong way? Well, it depends on who sets the objective, who chooses the data, and so on and so forth. Okay. Now let's go on with our example. This looks kind of simplistic, right? Why use only past convictions? Maybe there are other determinants, social, economic determinants of that particular person's context that can help us predict whether they're going to commit a crime over the next quarter or not. Okay? This is something that's actually been done in machine learning literature for the past 30, 40 years as model. And somebody thought, why not do it? Why not do it and help our judges and lawyers and so on and so forth, and make their life easier. When you have to look at 10,000 cases and you have to judge over 10,000 cases who might be likely to commit a crime, this is a very, very intensive work. Why don't we create this algorithm, make it learn, and help our judges decide using that if a person is likely to commit a crime or not, and just release the ones who are not going to commit the crime and keep in the ones that are likely to commit a crime. Okay? Now, this is something that if it sounds familiar, it should, because it was in use, and I think it's still in use. It's called Compass. And there's an article in 2016 by ProPublica where it shows how using these algorithms are extremely biased. And it creates it predicts wrongfully that black people are more likely to commit a crime and white people are less likely to commit a crime than they actually do. Where did that come from? We're going to walk through and show you that sometimes this is buried so deep in the algorithm that it's very, very difficult at first to understand why these results come out. And this is a cautionary tale for everything we do when we talk about large language models, when we talk about text generation, and so on and so forth. So let's take our model. We just learned our baby model that was just using past data. Now we have a large data set, that database for each individual. We know their education. We know their parents' education and income. We know their wealth. We know their income. They have kids, how many years they went to school, where, and so on. And so this is a very, very detailed data set. And we want to use all of these variables to predict if this person is going to relapse or not. So again, we set an objective. We take our variables and we want to predict recidivism and its degree, because several studies have shown that this can be done fairly well. But when we do that and we just pick up a model, we pay very little attention to social context and to the causality of those variables, something that generally a judge will be looking at when making a decision, not the algorithm. If we don't specify to the algorithm, I'm really interested about context, and then we have to define what is context. And if we don't talk about causality and we have to define what is causality, the algorithm is not going to look at them. And even us amongst ourselves have a lot of discussion nowadays, what is causing a person to commit a crime, if we can call it causality like that. Once we set our objective, we choose data, we register, we take this database of past offenses, we look at all their variables without looking where this data was sampled. So this, for example, is one of the biggest problems in this area. If you register data only in certain neighborhoods, the socio-demographic profile will heavily influence the results. Okay? So if you send the police only in black neighborhoods, but you don't send the police in white neighborhoods, maybe there's crime in white neighborhoods, but they never register them. This is where the sample is not representative. And you can think about this dimension. It doesn't have to be race. It can be ethnicity, it can be income status or level, it can be employment status, employed, unemployed. This shows up in almost every aspect of machine learning. We codify the functions, so we simply say use variables, these socioeconomic variables, to predict the likelihood, how likely it is that the particular person is going to relapse. And then we optimize over a parameter where we say, tell me which variables are very useful to predict, show me what is the error in prediction, and run this for the entire population that I'm giving you. Of course, here, it's hard to say we optimized over something. We picked up some human dossiers, if you want to call them like that. We have a lot of variables. We don't know necessarily they might be the right or the wrong ones because we haven't decided what's causally leading this person to commit the crime. What was the outcome in this case? So the ProPublica looks at this data and sees that misclassification reflects sampling bias, the stuff I was telling you before, mixing in with insufficiently tested causal mechanisms of recidivism. So black defendants are twice more likely than white defendants to be predicted to relapse than actual observation, so they're overly penalized. White defendants are predicted to be less risky than the actual behavior. This was 2016, and this brought a lot of discussion about the usefulness of employing these algorithms in practice in courtroom. There's a study in 2019 that's called ProPublica's Compass Data Revisited, and the author finds some inconsistencies in data processing, but these inconsistencies only marginally affect the results that are given above. So, we can say this is not something that's necessarily easy to understand, but keep in mind that you have absolutely the same problem in a private domain. If you work for an insurance company where you try to predict if a person is going to drive recklessly, you do it in a bank. When you give someone a loan, you want to understand if they're going to pay back or not, and so on and so forth. Everything that has to do with classification, yes, no, black, white, 0, 1, falls into this category of problems. What this whole thing shows us, and this is still an ongoing debate that brought on a lot of research, is that it's extremely useful to have open source data and algorithm. ProPublica wouldn't have been able to look at that had the data been behind a paywall. ProPublica wouldn't have been able to assess these likelihoods, these errors of the algorithm, if this algorithm was not publicly available. Okay? If we don't see the objective, if we don't see the function, it's very difficult to judge what's happening. It looks like it's good, but there's no way for us to judge this. Maybe it's just in the courtroom. Well, no, somebody thought in 2019-18 to use this same recipe to make money. Okay, it's something that we should have expected. So there's this company, Zillow in the US, that gathers a lot of data about the real estate market. It has access to detailed listings of a property, neighborhood, and a lot of other data about it. So what they thought is, look, instead of using a valuer, which is a person that stays there and considers how much is this house worth, let's use an algorithm and do this for 10,000 houses. Because if the algorithm is good, it's going to be able to detect those houses that are overpriced. We don't buy those, and those that are underpriced. We buy those and we hold until the market turns. So the recipe was the following. Put in place this machine learning algorithm, identify undervalued houses or having high growth potential, buy them all fast, renovate, and resell for profit. It sounds like an awesome recipe. This is what the machine learning actually looked like. It predicted growth linearly. So, if you take a puppy and you feed growth data of a puppy into machine learning algorithm, if it doesn't account for many things that happen over the lifetime of a puppy, it says, oh, from here to here, everything sort of doubled in size, and from here to here, almost everything doubled in size. Therefore, from here to here, which is the future and I don't know yet, everything must double in size. Okay, so you end up with some abnormality that, kind of doesn't look like the real thing. This is the outcome. So how Zillow got flipped by AI, it's a play of words, because in the US, when you buy a house, renovate it, and sell it quickly, you say you flipped the house. And in this case, AI seems to have flipped Zillow. So Zillow is selling 93% of Phoenix homes for less than it paid. So it's not just the data, and as soon as the algorithm is not transparent, it's very difficult to judge what's happening. When it's perhaps private money that's sort of trying out something, it's one thing. When you're thinking about human life, it's a completely different story. Now, this is how machines kind of learn. Okay, so we take away the learn and we put it between brackets. Keep in mind that what happens there is some human defines all those things, does all the math, the computer goes in, and within a very, very precisely defined list of tasks, give you some parameters. Okay, so just some math calculation that somebody does instead of on paper, does it on a computer. But it's important to understand how these computers see, hear, and understand, because it helps us judge what actually happens, for example, when a computer generates a contract for us. Why is that contract? Could that contract be good? Maybe that contract sounds like complete nonsense. As mentioned, anything a computer works with is zeros and ones. And let's suppose that we want to build a simple classification system using a neural network. This is a fancy machine learning algorithm to automatically detect if a car is registered in Estonia, Latvia, or Lithuania. It's a simple thing. You're at the police. There's, I don't know, 10,000 cars passing over your bridge. Let's suppose these are the only ones that are going about there. And you're going to have to decide if the car is registered in either of these three countries. What happens? Well, you're going to take a photo. And that photo is going to look something like that. And you might have these options. How does the computer understand if it's Estonia, Latvia, or Lithuania? Let's suppose it's Latvia. Well, once you take the photo, this gets converted, remember, in zeros and ones. That photo of us, this is what the computer sees. It actually sees a very large matrix of zeros, ones, and 05s. So if it's white, it's 0. If it's black, it's 1. If it's dirty or it's unclear because the lens was dirty or whatnot, it may be 05. Okay? So what's the computer going to do with this? Well, it's going to unfold this huge matrix. It's going to cut it up in pieces. Each column gets added to the next column. It creates a very, very long index, a very long list of numbers that has a lot of zeros, occasionally some ones. Again, a lot of zero, occasionally some ones. And it takes this and plugs in into a neural network. So this is what it looks like, but before you freak out about what this spaghetti place is, it's just a function. This is just a very large function that takes as input a lot of numbers, the zeros, 1s, and 05s that you get from here, and then optimizes for those values, omega, that help us predict, gives us probability, if this is an LV, an LT, or an EE. So what the computer gives us, just like compass, it gives us some probability of something happening. Okay, this probability, it looks at this picture and says, based on my optimizing work, I tell you that this number, this plate is 80% from Latvia, 15% might be Lithuania, and 0.05 from Estonia. Okay? These are generally made up numbers, but it's very likely that these two are going to be a little bit closer because the first letter is L, and the zeros and ones for L are going to look exactly the same. But once you get your engineer in, they can figure out ways to make this distinction even better. But this is what the computer eventually does. It takes the zeros and ones, it creates this function, and then it has some parameters, and you say, look at all the combinations of possible parameters which give me the smallest classification error. So it tells me the closest, what might be Latvia, what might be Estonia, what might be Lithuania. This is our input data. There's a hidden layer in the middle, and that's our output. And this is a prototypical neural network architecture. Okay. Again, we're using the same recipe. We set an objective to categorize. We choose the data, pixels from the picture. We codify the function. This is our function. And then we want this to maximize accuracy in categorization. Again, even though this looks like an extremely complex thing, and it can turn even more complex than this, at the end of the day, these 4 steps are going to be there. Okay? Whether we talk about our super baby tiny model or we talk about very large functions like this. Now, obviously, you realize where are the limits to this machine learning algorithm. As soon as somebody from a different country comes, it's not going to be able to categorize it. And if it's a well-done algorithm, it's going to tell you, I cannot categorize. But if it's a poorly done algorithm and you can't look at it, it might tell you it's Estonia, or it might tell you it's Latvia, or it might tell you it's Lithuania with very high probability. Okay? And this is where the danger lies, and this is what was the issue before as well. So open source data and open source algorithms, especially if we want to talk about public domain, are essential in this case. And you can immediately understand that, before but maybe about 10 years ago, each such question, I want to categorize license plates for cars, had its own dedicated neural network. So you had to go in and you had to have a different function, and you had to have a lot of data to fit in, and you would have this list of parameters, and that would be your actual important thing. But if you wanted to categorize cats and dogs in a Facebook picture, this would be a completely different story, and you would have to train another neural network with different data, maybe different architecture, and so on and so forth. So it's clear here that if you don't have access to the data, it doesn't matter if you have computing power and a good engineer, there's no way you get your good algorithm to work. Clearly here, copyright infringement looms large with most types of training data. And there's a prototypical example of how this can screw up and why life is difficult for a neural network. And it's this picture. And this is usually done to test categorization for pictures. If you want to train a new algorithm, it has to pass some tests. And this is the test like we do for students for a machine learning classification. You feed it this type of data, and it has to predict accurately if this is a muffin or a chihuahua. And you can kind of see immediately, I mean, for the guys sitting in the back, it's pretty difficult even for us to figure out which one is which. Okay. Now, we talked about image classification, but obviously, what we're very interested in is to go a little bit towards the speak and think idea. Now, the building blocks are going to be a little bit different, but at the heart of it stays the same recipe, those 4 steps, a neural network that's now a little bit differently thought. So let me show you how this is done and why this is done a little bit differently. So when people started to look at this in machine learning, they looked at large bodies of text, and they realized that there are certain regularities in large body of text. How do you assess these regularities? Well, you can sort of define a statistical function. So you can see how often certain words come together within, let's say, the page of a book or of a contract or whatnot. So this is how people started to think about this when they started to look at modeling language, turning into a function that the computer can understand. They had to first understand how words get meaning. And there's two, of course there's more, but two linguists that stand at the forefront in this case are the ones that have sort of gave this dictum that you shall know a word by the company it keeps. So meaning of a word comes from the words that surround it. So you can associate a word with some of the words in the same phrase, and you kind of understand what's the meaning of that. And we take this idea and we plug it into a function. We want to create a correlation table. So we want to be able to measure how often we observe a certain word in company of another word. And that has a particular name. It's a collocation, how often we see this word collocated with another word. And in the beginning, you would have these tables, large tables, that, for example, would give you for each individual word its collocates. So, for example, for bucket, you see here that F stands for frequency, how frequently we observe this together with, and you see that the most frequently encountered word with bucket would be water, so bucket of water. What's the next one? I'm looking down the list, might be wrong. Plastic. Okay, a bucket of plastic or a plastic bucket. If it's a verb, the most frequently encountered association is to throw a bucket. If it's an adjective, then it's going to be a large bucket or it's going to be a full bucket. And how are these things done? This is a very simple counting exercise. You take all of your body of text and you simply count how many times do I find in 1,000 words bucket together with water. Okay? Bucket together with spade, bucket together with plastic, with slop, with size, and so on and so forth. Okay, so this is a simple accounting exercise. But this accounting exercise is useful because it gives us something that looks like a probability. The more often a word comes together with another word, the more likely they are to be together. So this is something that is going to be more frequently encountered in normal speech, let's say. Okay. And that was a little bit the philosophy that started this. This is 1990 towards, and then these slides are from 2007, and the authors are trying to create some statistical functions for each individual such word. But keep in mind, when you want to do this, you have to create these large matrices for each individual word. So each word gets its collocation matrices, and this is going to be a large data set, a very large data set that needs to be produced, maintained, and so on and so forth. Why do we get the current revolution? This is not the technology that's currently in use. The technology that's currently in use is, of course, this is a super simple example, but it's at the core, it's another neural network that works again to predict. But now it doesn't predict if somebody relapses, if somebody defaults, and so on and so forth. Now it predicts the next word based on the word that it had before. So let's look at this. Let's take our body of text, that's our training data. We have two sentences. Riga is beautiful and Vilnius is nice. And what we want to do, we want our network to be able to predict that when we plug in Riga, it has to give us beautiful. And if we plug in Vilnius, it has to give us nice. Now, of course, this is super simple, but keep in mind, if you solve this problem and make this neural network very large, you can fit in not two sentences, but multiple sentences. That's your context window in your ChatGPT. And it can work with a multitude types of texts, larger sentences and more complex and so on and so forth. But before we get to that, we need, again, just like we did with images, we need to transform words into numbers. Remember, the computer just understands zeros and ones. How do we go from words, and more importantly, meaning, to zeros and ones? Well, we're going to start off by creating this matrix. Remember, here we have this function with weights. And what we want to do is to set a different objective. We are telling now our neural network that if you see Riga to be the selected word, now we have a 1, all the other ones are 0, then you have to predict is to be the next word. That's our first pass at the optimization. So the computer does this, and then it gives us some weights, this omega 1 and omega 2. And then this is our first step. It gives us this list of probabilities. Once you did that, and you take your own output is, and you fit it back in, now is 1, what I want to do is predict beautiful. Okay? So the ones represent the word that's been selected on the input. The ones represent the words that are indicated as the most likely to come out following that word. So instead of having these large collocation tables, we're now going to replace this and going to have large neural networks with the billions of parameters that are able to link words one after the other based, again, on the text that you feed it. So obviously, if you only give it text that's saying Riga is beautiful, it's only going to predict Riga is beautiful. If you give it only text that says Riga is not beautiful, it's only going to predict Riga is not beautiful. So what you feed it, this is what it's going to give to you. The training data is extremely important, and that's where your biases come from. Before, they were hidden in the way sampling was done. So you only go to the neighborhoods that have a certain type of criminality. Unfortunately, that was associated with a certain type of socioeconomic profile. You never sent it to the other neighborhood. Because maybe, the same crime was happening across the road, but the police was not there, nobody was reporting it. This is your data. Automatically, that type of socioeconomic profile is the most likely criminal. Here, if your text only says Riga is beautiful, and it's true, then you're going to only get this type of outputs. But this is something that's very difficult to check when your algorithm is feeding on millions and millions of documents, some of them from libraries, but some of them off the internet. And this is some of the things that are, some of the things that are inside. You just have to imagine that this thing runs over many cycles to adjust those parameters, and it's not just 10 or 3, here is just 2, but it's literally billions and billions of parameters on learning and so on and so forth. Once you optimized this, those weights are exactly the numbers that are going to give you the relationship between your words. And that's what's going to create your your meaning. So once you take this, so we just have omega 1 and omega 2, you can plot them together and you can have your meaning map for your text. So for example, after our algorithm learns, so optimizes those things and so on and so forth, and you plot them, you're actually going to see that the values that these words have inside are very similar. And here the algorithm learns something about Baltic capitals. And then these two words are going to have similar numbers. Here the algorithm learns that these might actually represent more or less the same thing. Now this is just two weights. Remember that in reality these algorithms work with billions of weights. And that's where meaning comes from. Meaning, in the sense of what the machine learning understands, is that somewhere in the space of a multitude of omegas, it finds relationship between words. So for example, Riga and Vilnius in this area could be about cities in the Baltic region. But if you had a third dimension, which was about economic growth, it would lump them together with, let's say, Prague, or let's say Budapest, which would be about high growth economies. Okay, so the words are put together in multiple clusters in a very high dimensional space, and that's where meaning comes in. Of course, now you say, okay, this is easy and this is done. Let's have this. Let's have this extended. And then once we have this thing, let's make this big algorithm some form of corporation or some form of decision agent, and we call it a day. It's going to be very simple. You don't have to do your homework. You don't have to write your contract. You don't have to write your law. You just ask this particular algorithm to do that for you. And at one point somebody brought up this idea of granting legal personhood to an AI system. But here, as soon as you look at it and you open it up, you realize immediately where the dangers are. And there's a lot of challenges with opaque complex systems, such as these ones. Some of them are open, many of them are not. Some of the more successful private solutions have only limited or no visibility. You have startups that give you large language generating models out in the open domain, but again, as soon as you go for pay, this is no longer the case. What did people do with this? Well, obviously it was just the thing we said before. Let's not, under the pressure of time and stress, let's ask ChatGPT to write for us a particular brief. And this is a case. This is an article from a few years back where lawyers submitted a bogus case created by ChatGPT, and the judge fined them $5,000. Why is that? Well, because sometimes these large language models invent things that are not there, or they hallucinate. So they tell you some facts, or they tell you some persons, or they tell you some causality links that are actually not present. They simply invent things, because remember, the only thing that they do is, even though you don't see it as the user, it creates a large list of probabilities of words, and what it gives you as the final user is the most likely word. But where is that most likely coming from? Well, it's coming from what it saw before. Maybe it makes no sense. Maybe it was just fed bad cases written by students. You didn't know. Nobody checked them. It learned the parameters based on that, and when you actually go and do things, it's just going to give you very bad outcomes, but it's not going to warn you. Remember the problem with the license plates. If it sees a license plate it doesn't understand, and it's not programmed to say, I don't understand it, you're just going to say something. It doesn't mean it's right. And now again, this is not a trivial thing, but there are some solutions already in place, and more solutions are being generated to deal with hallucinations. But overall, this is where things stand. There's some interesting work on this to understand why LLMs hallucinate in the way they do. And some people took a lot of time to understand where exactly this comes from. And most of the time, this is not about the algorithm itself, it's about the training data. So some of these hallucinations have been found to be just some random stuff people wrote on a forum, on a blog. So the LLM is trained by crawling over the entire internet. It makes no distinction between this is good or bad. It makes no distinction this is right or wrong. Factually right or wrong, not morally right or wrong. Morally right or wrong is 10 times more complicated. And it just feeds off. Somebody says, oh, I know how to fly to the moon by, putting gas in this and they're burning it up. It says, okay, this is a reasonable solution. I'll just take it and plug it in. I'll give it to you as a reasonable solution. Because reasonable is not something that's defined inside of the objective function. The objective function is just predict next word. It's not predict next word that's reasonable. That's much more difficult to do. Okay. Now, there are interesting parallels to the distributed ledger technology solutions that were tried out before. And I think even though everything is a little bit on fast forward in AI, there's some interesting lessons that come from this cryptocurrency, from many cryptocurrency initiatives. So just a step back, again, we talk about a technological innovation. This is a coordination system for processing and storage of sensitive data, open to everyone without a central figure, so without a central point of failure, which is achieved by simply fixing some rules on how data is accepted, how data is written in the blockchain, and how data is processed. That those rules are enforced through code, so they're simply programmed into a machine, and that enforcement basically is done to prevent data and rule alteration. Of course, this is a very, very high-level, loose definition, but overall, just keep in mind that every time you write something in an Excel, you're kind of doing some of these things in a centralized system. You open up the Excel, you change it, this is something we don't want, then you have to create some rule to make sure that what data is inputted by one user cannot be altered by another user. And you want that data to be open, and you want it to be accessible by anyone. So you take that philosophy, let's say, and you think about it, oh, if I write my data in the blockchain, everybody else is going to be able to see the data, but not my personality, not my identity, sorry. So this is a little bit where this, how this is set up. And these things come in with different functionalities. So there's different blockchains that have different priorities. Some are about increasing decentralization. Some are about ensuring anonymity. Some are designed to improve autonomous execution of scripts, such as smart contracts. These priorities, again, of the user are reflected in the architecture of the blockchain. That means in consensus mechanism, how people agree on which data must be entered, how people agree how data is processed. On access rights, who can access on the blockchain. In the case of public blockchains, anybody can open up an account, between brackets account, a wallet, and can access it. In the case of private ones, you have to be given access rights. So a lot of these things have various degrees of design choice. So, for example, if you look at Bitcoin, it puts a lot of emphasis on anonymity and censorship resistance. If you're looking at Ethereum, it puts a lot of emphasis on functionality by enabling smart contracts. These are perhaps the two more commonly known ones, but there's a lot of other ones that try to tweak these parameters of anonymity, decentralization, and so on and so forth, and give you your, if you want, your flavor of a blockchain. I picked Ethereum just very quickly because one aspect that's very interesting there was the potential use of smart contracts. So here, if you take a look at the prototypical example of a blockchain, again, it's just number and functions, but remember, they're done in a particular way to be able to achieve a particular outcome. So here, remember that you don't see the identity of those transacting. So that's going to be just a long rows of numbers and letters that make absolutely no sense so that you can't understand what's happening. And they do that by employing these fancy functions called hashes that hide the data behind this very long-looking rows of letters and numbers. This could be the identity of the sender and the receiver, as well as the amount that's being sent. This is being written in this blockchain together with a bunch of other things, such as the date when this was executed and the hours. And the transactions that go in a particular block, this is what they would look like. So this would be a from, to, and the amount. And these are just some hidden identities that we do not see, but we just see maybe the numbers that are going from one to the other. Okay. And when the blockchain registers this data, what it does, it simply inscribes in this database, which is then distributed across all the computers that are working with it, that from this account, we deduct 11 units of Bitcoin and we credit them to this account. Okay. The data related to all of these transactions in this block are given a special signature. This is what this hash is. This is a signature that you cannot alter. If you want to change the sender, the recipient, or the amount on any of the transactions inside, the signature is going to be changed dramatically. And there's no way you can do that unless you do that for all the computers that are running this at the same time. Okay, so this is why it's the blockchain. We say it's censorship resistance. You can't actually go in and censor certain things. Change resistant. You can't go in and change, and you can't prevent somebody from transacting as long as they have access to their account. Okay. Once you have this is linked together one after the other. Each transaction is linked one with the other. And these transactions, all this information is distributed on all the computers, all the servers that are running a Bitcoin node. Okay, so as soon as these are accepted, these transactions here, they go in and they're linked to these transactions here. And what I want to raise your attention to that at the second block, which is going to be 10, so this block was at 11:15. This block comes about 10 minutes later. This block is going to take the previous hash, so that the digital signature of all the transaction and users that transacted, this number here, is the number identifying them. So if somebody wanted to change something in a particular thing here, this would produce a different hash, which would not be recognized in the second block, and would immediately be repudiated. Now, the important thing is to remember all of these things are exactly the same on all of the computers in the network. This is where the decentralized nature comes in. Once you have your data structure placed like this, the good thing is you can also create little bits of code that can read that data and execute certain transactions automatically. And these what are smart contracts. This is if we talk about Ethereum, these are bits of contract that can read data from the blockchain and can write data back to the blockchain based on some conditions that you specify and you program. Remember, computers only know zeros and ones. And the interesting thing, 2016, 17, we had this big discussion that smart contracts will reduce the need for legal services in blockchain-enabled transaction, where the economic rationale behind it was simply that lawyers are very expensive, and they can be very expensive for small transactions. So why not try to replace that functionality by codifying, putting in a function, something that the lawyer does. What does the lawyer do? Well, it checks some conditions, it thinks about some things, maybe the smart contracts can do the same. This was the promise. What we ended up with is that we replaced expensive lawyers with expensive lawyers and expensive IT engineers. Because obviously in a blockchain contract, you not only have to understand the underlying rationale of the economic transaction, the way it's been done for whatever 300 years, now you also have to understand how this is codified. Is the smart contract on the blockchain really reflecting the contractual philosophy that's on paper? This is what this is the simplest smart contract example. So most of you are lawyers, you can look at it. Do you feel this is something you could work with? Not necessarily. And this is simply a function that tells a particular node to release coins to whoever asks them. Okay. And programmers have these things called commands. You can put in some words that explain what this function does. Okay. So these are the commands. This is open domain also, so if you guys want, you can check there. And this simply means that you, as a lawyer who are interested in automating this, you have to spend a lot of time, apart from whatever you're doing daily, to also learn how to program and to make sense of the programming language, to figure out if the functionality that is in the programming language reflects what you normally know happens between two contracting parties in a blockchain. Here already we saw some clash between cultures of these two industries. Language generally is loose, and ambiguity of law is something that's a feature. It's not a bug. You don't want to eliminate that completely. Just as the blockchain initially came out as a fully decentralizing solution, at some point we ended up with a lot of centralizing features. So if you look at blockchain transactions, after 2008, 2009, there's very few transactions on the Bitcoin blockchain. Why? Because they were purely peer-to-peer. People would meet up in coffee shops, would meet up at particular places and at particular times to say, oh, how many Bitcoins do you have in your wallet? Let me give you my address and you can send me your Bitcoins. Transactions actually took off once we had centralizing elements, such as exchanges. These exchanges are simply replicating exactly the same thing that the financial market does. It brings together supply and demand. And initially it came out as a fully decentralized revolution, but it adopted a lot of centralizing elements simply to make this thing work efficiently and at low cost. So in the same way, when we think about that this ambiguity of law is needed to provide flexibility when interpretability according to legal principle is needed. Institutions are social contracts. As soon as you don't agree with somebody about a particular contract, maybe you go to a mediator, maybe not. How are the mediators going to look at that? This is, again, very much socially determined. On the other hand, code is strict. It only understands zeros and ones, and it only understands functions it can optimize. So, for example, simple challenge, how would you transform into a function reasonable wear and tear? So, for example, when you rent a car, when you rent an apartment, there is normally a clause that says, okay, you give me whatever 2 months worth of rent as deposit, and you give it back, and I give it back to you if the apartment is in good condition, subject to reasonable wear and tear. So of course you have to stay 2 years in. Nobody expects that there's going to be no little dot on the wall, no little scratch on the floor. That's reasonable wear and tear. But what is reasonable? Okay. And then reasonable might be something in the north, might be something very different in the south, something completely different in the west and in the east. Smart contracts they don't understand that. So you have to think that inside your regular contract, you're going to have at least 5 or 6 such clauses that are ambiguous for a reason. I at one point thought that, with the advancement of machine learning technology, you're going to have pictures of what is considered by people reasonable wear and tear. So, you're going to have 1,000 pictures of scratches on the wall. That's reasonable. Another 1,000 that's going to be unreasonable. And then, you can look into that and compare the pictures and again say the same thing. I don't think it's completely out of this world. It could work. It works in some cases for some industrial applications. But again, as soon as we come here, it's a completely different feel. So this is just, they come in different flavors, the blockchains, and they give you different functionality. There's a lot of applications where they are active. So cross-border transactions, and now you see this not just between large companies, but also for financial transaction in tokenization. There's data products being offered. I chose one example where the blockchain depends very much on both user and institutional quality, the land registry and the cadastre. So there were some initial ideas to move the land registry on a blockchain, simply because today, if you think about purchasing a piece of land or an apartment, this is a process that involves a lot of back and forth on documents, from negotiation all the way to accepting a mortgage, signing the contract, and so on and so forth. So it's generally quite inefficient, it's quite costly, it's prone to manipulation. So, you know, a little thing changing in the document, if you don't pay attention to it, again, changes might change very much your contract. And it's also incompatible with the digital economy. You can't actually say you're digital if you send someone a PDF and you request it to be signed and brought back on paper, stuff like that. So if you don't have this automated access to the data and the underlying function, which is this API, this means that the entire purchase and sale will depend on multiple parties exchanging these documents multiple times. So since 2016, there's been a lot of projects on this. So it's Honduras, it's Ukraine, it's Georgia, it's Sweden. In US, there was one using the Bitcoin blockchain for registering transactions and so on and so forth. In some cases, it was deemed as unnecessary or too costly or not adequate for the function that it had to provide. This is the Vermont case. Some things have changed since then, but at least the initial stages, it was not deployed as indicated. And I picked two countries that have had these pilots just to show you that it's technology, but it's also the user and the institutions. So Sweden and Ukraine had very, very different reasons to move their land cadastre on the blockchain. Sweden wanted to move it simply because they want the younger generations who grew up with cybersecurity, transparency, and digitalization to know that they can trust their government. The alternative, and this is the statement of the Chief Digital Officer of the cadastre, is if we don't do it, they will trust companies like Google and use a future land register app that they're surely working on already. So here, in a sense, the public authority says, look, there's going to be at some point a legitimacy question. If the private company is able to offer something that we're no longer offering efficiently, we're not going to be able to maintain, let's say, our credibility in this area. And their solution was a mix of decentralized and centralized technology elements, where the registration of the new owner after the sale contract is signed is reduced from months, about 4 months back then, to only a few days. So clearly there's an efficiency gain there to be had. As soon as you have digital signature for all the parties involved, you go from months to days. It's also a matter of cost. And again, it's a matter of credibility. So this was Sweden. Let's do things digitally because the young generations want to do things digitally, and you know, the private entrepreneur might actually give us something better. And let's go to Ukraine. In the case of Ukraine, the old system was a private solution, not really under government control, where inputs in the cadastre were forged. There were fictitious transactions. There was large-scale fraud, especially with the land of the state that had valuable mineral and gas reserves, and so on and so forth. So there are some horror stories where people wake up in the morning and they're no longer owners of their own apartment or their own land plot simply because somebody else wants to build a mall on top. And this was not in the hands of, technically, was not in the hands of the state. So there was an attempt in 2017 to do blockchain. Because obviously, if you bring in a blockchain, you can see immediately my land title is valid. Yes, you can just check it on your phone. You don't have to go to someone's office and somebody has to open a book which might actually be forged or not, and so on and so forth. But actually, the 2017 failed due to lack of institutional support. If you want to do that, you have to have multiple parties interested in moving that from the state itself. So in that case, the 2017 solution didn't work. There was a second attempt in 2020, which was actually successful. There was an audit. that brought up all these big problems to light. I think at some point they estimated that a surface area of Slovakia was forged inside of the land registry, land cadastre in Ukraine. And this led to a centralized solution which supported the launch of the land market in July 1st, 2021. It added a lot of transparency benefits, so you're not at the level of being able to check exactly like you would do in a blockchain, but it brought a lot of flexibility and a lot of transparency compared to the old solution. So in this case, and if we go back to this this blockchain wave of innovation, this kind of puts the private interest against the regulatory interest. There's a dilemma identified in this area. It's called the Collingridge dilemma, which is simply saying, should we regulate technology early while it's still developing, or should we do it later when control is more difficult because of user adoption, integration with other technology, and so on and so forth. And this is always a difficult task because obviously if you're an economy that's interested in supporting innovation, if you regulate too early, you might constrain your innovator to keep certain types of solutions off the market, not to test them, and so on and so forth. And again, here, this is perhaps a US versus Europe type of different culture. Perhaps in the US, there's a little bit less intervention in the early stages, a bit more later on. In Europe, perhaps is the other way around. I think there's an interesting case if you look at that is to look at Lithuania on fintech. This initiative started late 2016, 2017. Some risks were identified, but I would say clearly there are benefits if you look at the number of companies established, workplaces created, and so on and so forth. No technology comes without risks, but in this case, if you can more or less identify them, I think at some point it's interesting to consider this simply as a trade-off. There's some inherent risks to every technology, so the only trick is to have the proper institutions to manage them, to evaluate them and to manage them. Right. So that's not we're a little bit ahead of schedule, but that means we only have a little bit more time to have questions and discussion. The important thing to see here is that when we talk about AI and law in general, there's a bunch of principles that are very difficult to innovate in a technological sense. So, for example, ambiguity and discretion are there for a reason. For example, if you look at fair use doctrine in copyright laws, if you look at the previous example of reasonable wear and tear, if we look at the Howey test when we talked about ICO, these are fairly loose tests that are there because you don't want to have regulation designed for every little innovation. You would rather have something that's somewhere in between. If it catches on and the user adopts it and it's economically feasible, then you can think about new institutions, then you can think about new regulation and so on and so forth. If you look at the EU's approach, this has been very balanced. We didn't get the MiCA until several years of testing by both private and public. Central banks have dedicated spaces where you as a company can go and test these things. Large banks started to build on these, integrating both private and public solutions. So there's clear benefits there. What do? You don't immediately come with a regulation that would have killed it. You start gradually introducing elements using the old regulation or interpreting the old regulation until you figure out if it makes sense, and then you bring the new regulation or new institutions or new laws, and so on and so forth. The important question here is, do we want to do away with core legal principles and doctrines for the sake of efficiency and speed? Because this is most of the time what's being marketed as one of the big benefits of these things. Yes, they can be fast. Yes, they can be very efficient. They might cost very little. So if we go at Compass, it can definitely give you predictions for 10,000 people within minutes, but what are the costs of those things being wrong? And on that side, once you start thinking in terms of costs of technology error, these are not going to be they're not going to be so efficient. What's clear though is that AI is already changing profoundly markets. So this will challenge lawmakers and enforcers because it makes certain harms undetectable or prohibitively expensive to contain. For example, if you're looking at financial markets, there are now algorithmic trading that leads to collusion as the natural outcome. These are functions that are optimized, trading with other functions that are optimized, and the outcome that they come to is actually collusion. And this is not done because it was programmed, and this is the interesting part. It's not that somebody said in their programming function, in their objective function, send signal to that algorithm. If it agrees to price X, you trade on X. This is not there. This is simply that when they're optimizing exclusively for profit, it ends up that an AI agent will collude with an AI agent on the price. Who's then to blame? Can you blame the person that programmed it? The person that keeps the computer on while it's running? These are not easy, immediate questions to answer. Generally, institutions and public functions that involve discretion and value judgment will require a human in the decision loop. Legitimacy of public authority rests on transparency and accountability, and generally that accountability is achieved through, of course, what is arguably an imperfect political process. But obviously, when we think about replacing this imperfect political process, we have to ask ourselves with what? What is better? And, here the danger is simply that, we're going to end up with an AI republic governed by a tech visionary that says you submit to be judged by an AI court if you want to live in my city. And, here it's immediately must come to your mind, what do you mean by that? Well, some people are arguing that we should have AI judges because they're going to be very equilibrated, they're not going to take sides, and so on and so forth. But just like we had the Howey test for ICOs determining if a coin is a security or not, somebody will probably think, oh, let's do an AI culpability test. Okay, maybe not for an AI judge, but maybe for an AI robot that works at home. So if the robot kills you, can we say that the robot is to be blamed, or should we say that the manufacturer is to be blamed? I think the manufacturer will put a lot of emphasis on bringing culpability to the machine, not onto itself. But when you think about an AI culpability test, can you think what it means to define mens rea actus reus for a machine? With this, we have to give value judgments to a machine. Does the algorithm know what's good or bad? And why did it act on the way it acted? So these are things that you see immediately that come a little bit in brings the two cultures in contrast. Generally, lawyers and judges look at a word and see 10 different meanings. AI engineers look at a word and see only one meaning. There can be only one meaning because the computer does not see otherwise. You want more meanings, we have a list, but you have to say it. And many of these things are sometimes perhaps difficult to transmit because sometimes they lie hidden somewhere in the code, and only 4 years later you realize that they've mislabeled a person as being dangerous or a person as being not dangerous only after somebody looked at the data, only after somebody looked at the code, and so on and so forth. So in general, there's a lot of benefits. It's already out there, and I think it's going to come back to us as lawmakers that we're going to have to act. I think this thing here is already being tested. So for financial stability reporting, for example, central banks are looking at automated agents that can create end-of-day reports. It's not unreasonable to think that certain functions will be automated in there. So we're going to have AI agents that oversee certain functions, that evaluate certain risks, not take decisions. That should still be the human, but they're already able to do this fairly efficiently. So the question is just to find the right balance between the human intervention and algorithmic autonomy. That's a bit all on my side.